This example comes out of section 9.2, Analyzing Rational Functions. So this example is a teaching example, but it's also kind of a test style of question where we're asked to match the graph with the function. We're given three functions, all rational functions with denominators, some simpler than others, and then three different graphs. And the idea is to try to match the function that goes with the right graph. This question could be asked in a diploma exam or an exam, probably in a slightly altered way, just because they don't really want you just to be able to plug something into your calculator and see the answer that simply. So they might switch some numbers for letters here so that we couldn't put in, for example, x squared plus b over whatever instead of x squared plus 2. But let's just talk about it in terms of the ideas. First of all, I would suggest factoring everything that you have, everything that you can factor. So to factor f of x, the numerator actually doesn't factor. It's a sum, and no common factor, no nothing. And we have x minus 2 times x plus 1 in the denominator. So even just looking at the non-permissible values, my non-permissible values for that one are x can't equal 2 or negative 1. So that in itself would answer part of my question, but let's keep going with g of x. So g of x could be written as x minus 1 over x minus 1 times x plus 1. So again, just looking at non-permissible values, x can't equal plus or minus 1 for g of x. For h of x, we have h of x equal x minus 3 times x minus 2 over 3 minus x. And our non-permissible value is that x can't equal 3. Just looking at the non-permissible values, we'd be able to actually answer this matching question because they didn't make it too hard on us. They could have made it harder where one graph had non-permissible values at 2, negative 1, and so did another, but one of them had points of discontinuity and the other one had asymptotes. But in this case, the only graph with non-permissible values at 2 and negative 1 is this one here, so this one must be f of x. The one with non-permissible values at negative 1 and positive 1 is this one here, so this must be g of x, and by elimination the only one with non-permissible value only at 3 is h of x. Looking a little closer why these non-permissible values are what they've become, g of x is probably the most interesting one because it's the first graph we've looked at that has both a vertical asymptote and a point of discontinuity on the same graph. And g of x is kind of an interesting function because it has one factor that does match the numerator, which means that at x equals 1 we have a point of discontinuity, and that is this point right here that's at 0.5 I believe. But we also have another non-permissible value that doesn't have a matching factor in the numerator and gives us a vertical asymptote at negative 1. The h of x is also somewhat interesting in that some students have trouble seeing that when h of x equals x minus 3 times x minus 2 over 3 minus x, we can actually factor out a negative and call that negative x minus 3. And so even though they didn't look like they were matching, it turns out that the x minus 3 factor is common in the top and the bottom, and that's why this turns out to be a point of discontinuity and not a vertical asymptote. So an interesting question, the way it's worded obviously would make it, if it was exactly like that on a test, it would be pretty easy because you could graph them and just say, oh, f of x goes here, g of x goes here, h of x goes there. But understanding what the difference between points of discontinuity and vertical asymptotes is kind of the whole point of that section.